Complex numbers Argand diagram. So when we talk about a complex number itself, there are two parts to it. So it tends to be classed using the letter Z, and that complex number is broken down into two parts, the real part and the imaginary part. And the real part is the constant, and the imaginary part is the part that contains the letter I. So often we see the real part written as RE of Z, where Z is the complex number, and IM, the imaginary part of Z, the complex number. So it's important to note that B is the coefficient of I. So for instance, we could have the complex number 3 plus 2I, then 3 would be the real part and 2 would be the imaginary part. So the Argand diagram is the way in which we plot the complex number itself. So it's a bit like plotting a coordinate out to X and up to Y, where the horizontal is the X-axis and the vertical axis is the Y-axis. So in the Argand diagram, the horizontal axis is the real axis and the vertical axis is known as the imaginary axis. So if we want to plot the point 3 plus 2i, it's pretty much the same as plotting the coordinate 3, 2. So that means we go out on the real axis 3 units to the right, and we go up 2 units on the imaginary axis. And therefore that would be the complex number 3 plus 2i. Now if we connect from the origin to the complex number 3 plus 2i, this would be known as the length of the complex number, often referred to as the modulus. And the modulus can be represented by the letter or. Now, if you notice, if I drop a line down from the complex number 3 plus 2i, then I create a right angle triangle. And therefore, I have the opposite and the adjacent. Then the modulus, you can see, is actually the hypotenuse side of the right angle triangle. And therefore, the length, in other words, the modulus, can actually be found using Pythagoras. So what we end up with is the square root of 2 squared plus 3 squared, in other words, root 13. So in other words, the length of this complex number 3 plus 2i from the origin to the complex number itself is root 13. So this can be represented by or, as I said, or z inside the modulus symbol, because obviously the length of a complex number can never be negative. It's always going to be the absolute value, in other words, the positive value. Just a thing to note before we start looking at different types with the Argand diagram is that if we're talking about the set of numbers, we have n representing the set of natural numbers, z representing the set of integers, or representing the set of real numbers, and c is now going to represent the set of complex numbers. And if you look, when we draw our diagram, n is a subset of the integers, z is a subset of the real numbers, and the real numbers then are a subset of the complex numbers. So in other words, the imaginary part can never exist inside or z or n. Instead, it can only exist inside c. So if we wanted to plot any complex number on the Argand diagram, we've already seen one example there. But if we look at another one here, we have 7 minus the square root of minus 81. So that is a complex number in disguise, because obviously the square root of minus 81 is the square root of 81 times the square root of minus 1. And that simplifies down to 9i. So in other words, 7 minus the square root of minus 81 is actually the complex number 7 minus 9i. So that means I would go out 7 units on the real axis and down 9 units on the imaginary axis. And I would end up then in the fourth quadrant. If I was to plot minus 2 minus 3i, I would go out minus 2 to the left on the real axis and down minus 3 units on the imaginary axis. In other words, I would end up in the second quadrant. And you can see if I join the dotted line all the way back from the complex number to the origin, that would be the length of the complex number, in other words, the modulus. So type 2 is finding the modulus. So it's important to note there that we saw when we had the diagram, it's very easy to see that we were getting the hypotenuse of the right angle triangle. So we have to remember that, because obviously if we're not given the diagram, we have to remember that that is the modulus. In other words, Pythagoras formula off by heart, because there is nowhere in our maths tables that actually tells us the modulus is equal to the square root of a squared plus b squared. So you have to remember that it's Pythagoras. So if I have find the modulus of 7 minus 9i, I have to recognise that those lines outside 7 minus 9i imply the modulus or the length of the complex number. So if I get the square root of 7 squared plus minus 9 squared, making sure the minus 9 is inside the brackets, not outside the brackets, then I end up with 49 plus 81, which gives me the square root of 130. I cannot simplify this third any further, but if I could, you would have to, because again, you won't get full marks unless it's in its simplest answer. So if I get the modulus of minus 2 minus 3i, then this would be the square root of minus 2 to be squared plus the square of minus 3. And that, of course, gives us the square root of 13. The third type that we looked at today then was finding the unknown. So sometimes we can be given information about the modulus, and we have to use that then to work backwards to find the letters that were part of our complex number. So here I'm told that Z1 is a complex number, P plus 8i, and Z2 is another complex number, T plus 8i. And I'm asked to find P and T, given that the modulus of Z1 is 10, and the modulus of Z2 is twice the modulus of Z1. So what that means is that Z2 is twice the length of Z1. So what I would do is take Z1, P plus 8i, and I find the modulus of it, which is the square root of P squared plus 8 squared. But I was told that the modulus of Z1 is 10. So by equating those, I end up with the square root of P squared plus 64 equals 10. And if I square both sides, that gives me P squared plus 64 equals 100. And therefore P squared equals 36. And therefore P is equal to the square, or is equal to plus or minus 6. Because of course 6 by 6 is 36, but minus 6 by minus 6 is also 36. So I'm now going to use that information then to find T, because I know that Z2 is twice the modulus of Z1. So I know that the modulus of Z1 is 10. So that means that Z2 modulus is twice 10. In other words, the length of the complex number Z2 is 20. So if I take the complex number Z2, which is T plus 8i, and I get the modulus of it, that actually should... So I just get rid of those modulus signs there. They shouldn't be there. So Z2 is equal to T plus 8i. So the modulus of that then is the square root of T squared plus 8 squared. But of course I have already established that that's equal to 20. So by equating the square root of T squared plus 64 equals to 20 and squaring both sides, I then get T squared plus 64 is 400. And therefore T squared is equal to 336. And if I get the square root of both sides, I get the square root of 336, which simplifies down to 4 root 21. And of course, because I'm getting the square root of a number, I have to make sure I have plus or minus in my answer. Z1, it would be 6 plus 8i or minus 6 plus 8i. And Z2 then would be 4 root 21 plus 8i or minus 4 root 21 plus 8i. So for homework then, we were working on page 284. And then we looked at, well, what happens when I add or subtract complex numbers. So if I was to add complex numbers, I treat it the same way as I treat algebra when adding x's and y's. So in other words, we add like terms. So if I have 3 plus I minus 2 minus I get rid of my brackets, which is 3 plus I minus 2I minus 3 times 2 plus I. So I multiply out the brackets again, same way as I would in algebra. So that gives me 2 minus 2i minus 6 minus 3i. And then adding like terms, I have 2 minus 6, which is minus 4, and minus 2i minus 3i, which is minus 5i. If I look at Z1 equals 2 plus 3i, and Z2 equals 5 minus 4i, sometimes we can be given the questions in terms of z's. So, for instance here, find Z2 minus Z1. So I take the two complex numbers and I replace the Z2 and the Z1 with 5 minus 4i minus 2 plus 3i. So then getting rid of the brackets, again, it's minus 2 plus 3i, so that's the same as saying minus 2 minus 3i. And then adding like terms, so adding the constants, so 5 minus 2 gives me 3, and adding the i's, so minus 4i minus 3i gives me minus 7i. And then to finish off, you were doing page 288, questions 1 and 2.